let's make a start. Let's make a start on this. Say if you've got this type of differential, this type of differential equation is particularly used in simple harmonic motion. How would you solve that differential equation of this type? Yeah, if you look at any oscillating movement, okay, simple harmonic motion, something like this, some object moving horizontally or vertically, whatever it was, this one's moving horizontally, and the distance x satisfies this differential equation you normally find, or d2x dy squared is equal to, you know, how would we satisfy? How would we solve that differential equation? Yep.
Use a quadratic.
Yeah, let's have a look at the quadratic. Yeah, the characteristic equation. What do we get? If we look at the quadratic, what do we get?
1 plus
Sorry? Yeah, m squared. Yeah, m squared plus k squared. Yeah, plus k squared is equal to 0. Yeah. Okay. So what do we do next? Yeah. Well, okay. That's what we're going to do. Yeah. How do you solve this? Yeah, move to the k to the other side, so you get m squared is equal to minus k squared. So what is m equal to? M is equal to square root of minus k squared. So what do we get? J, plus or minus jk, isn't it? Yeah? Okay, so this is, what sort of roots have we got this time? Complex, haven't we? Yeah? This is, you can write this as naught plus or minus jk, can't you? Yeah? You can write it that way, can't you? Yeah? Naught plus or minus jk. Let me see this. Okay. Naught plus or minus jk, so it's complex. So you've got m is equal to alpha plus or minus j beta. What is alpha in this case and what's beta equal to? Yeah, alpha is 0, yeah. Alpha is 0 and beta is equal to what? Sorry? Yeah, beta is equal to k. So my solution y is equal to what then? What's it going to equal? Y is equal to what? Sorry? Yeah, it's definitely, the general solution is definitely going to e to the alpha x. So in this case, it'll be e to the naught x, wouldn't it? Yeah? Yeah, and then what? Yeah. A cos beta x, yep, plus b sine beta x, isn't it? Yeah? Okay. Now, what's e to the naught x equal to? It's 1, isn't it? This is equal to 1, so we end up y is equal to a cos beta x plus b sine beta x. Okay, so if you've got a differential equation of that format, then the solution is given by that. Yeah, that's your solution. Y is equal to a cos beta x plus b sine beta x, where beta is equal to k, that value there, isn't it? Yeah. Which is equal to, I should have put cos kx plus b sine kx, isn't it? Yeah. Okay, so differential equation of this format: d2y dx squared plus k squared y is equal to 0 gives the solution y. Gives solution y is equal to a cos kx plus b sine kx, yeah? That's what you get, okay? So, let's say you want to solve this one, a problem in vibrations, okay? Something oscillating, about some mass, okay, oscillating about the point, going up and down, or left and right, not up and down, and you're just given by this differential equation. Let's solve it. You're given some initial conditions, so you're told that, fresh page. You're told that d2x dt squared plus 25x is 0, and you're also told when t is 0, x is 1 and dx dt is 10. Oh, is it air conditioning on or something? No, it's something it seems to making a noise. I didn't realise in the first hour. So, how do we solve this differential equation then? How do I solve this differential equation? Yeah, you could put m's, you could do all over again, but you don't need to. If you've got something of this format, you know, this is what we done just a minute ago. Yeah, if you've got something d2y dx squared plus k squared y is equal to 0. Yeah, okay. You could say y is equal to a cos kx plus b sin kx. Yeah, you can use that directly. You don't have to keep on doing it each time. So what do we have? Have we got this? Have we got that in this place? In this case or not? Yeah. How can we write that? Go on.
We can put it as 5 squared.
5 squared, exactly. We can write this d squared x, yeah, gt squared plus 5 squared x is equal to 0. Yeah, that's my k, isn't it? Yeah. So k is equal to what? What's k equal to? 5, isn't it? K is equal to 5. So my x is equal to what? K is 5. So what is x equal to then? Yeah, a cos what? Sorry. 5x, yep, plus, yeah, b sine 5x, okay? Why is this a useless solution? Sorry? No, x is not the problem. X is not the problem, something else is the problem.
You still haven't got A and B.
Yeah, you have got A and B, have we? Yeah, okay. We want to work out A and B. It's just, like I say, if it's a real life, I mean, in this case, it is a real life problem, a vibrational problem. Sorry? Yes, it should be in this case, yes. 5t, yeah. Of course, in this case, it should be 5t. It's a useless solution to you because you don't know what A and B are, yeah? Okay? So how do we find A and B? How do we find A and B? Substitute what? Yeah. T is 0, x is 1, yeah? Okay? So we've got, when x is 1, we're told t is 0. So 1 is equal to A cos 0 plus B sine 0. What's cos 0 equal to? That's equal to 1, and sine 0 is equal to 0. So you've got A is equal to 1, haven't you? A is equal to 1 because cos 0 is 1 and B sine is 0, isn't it? Yeah? All right, but that's no good. Why is that still not? That's still pretty useless. Go on, Patrick.
Because we don't know what D.
Yeah, we still don't know what the value of B is, do we? Yeah. How can we find B? How can we find the value of B then? Go on then, Henry. We could do that, but that won't help you get B. Something else you need to use. Go on, Hannah. No, that's going to be the same problem as what Henry's just saying. Let's have Mohammed. You don't answer too many. You're normally late. I have to have a go at you, so this time you're on time. So go on then.
Yeah, you use the dx over dt.
Yeah, exactly. We want to use this other dx dt is equal to 10, isn't it? Yeah, we want to use that, don't we? Yeah, dx dt is equal to 10. So we've got x is equal to this. So what's dx dt? How do we find dx dt? If we differentiate this, what do we get? Dx dt is equal to what? What do we get? Come on, you should be differentiating. These are the ones I told you to learn. You know, the cosine, sine, e. I said you should be, these derivatives should be at your fingertips.
-5.
Yeah, -5, go ahead.
Sine 5t.
Sine 5t, yep.
5b.
Plus 5b cos 5t. That's right, okay. What are we told? What do we know? What information do we have?
We have dx equals 10.
Okay, yeah. Why are you late?
Opticians.
That's not good enough. You've got to arrange some other time. Yeah, 10, yeah? -5a sine 0, yeah? Plus 5b cos 0. Come on, hurry up. Take a seat. What's sine 0 equal to this time round? Last time, guess what? It was 0. It's still 0, according to Rob. Does anyone want to talk about cos 0 this time round? It's 1 this time. Rob is saying that again. He's saying the same value. Okay, it hasn't changed for some reason. Okay, what do we get? We get 10 is equal to -5a. No, we get 0, don't we? Sorry, that's 0. That is 0 because that's
Then
plus
5b.
5b. So, oh, sorry, you can't. Please shout if you can't see. So, what does b equal? So, what does b equal? 2. Yeah, 10 over 5, which of course is 2. So, what's our solution going to be? What's our particular solution? There it is. X is equal to what? You tell me. Sorry. Anyone? Anybody?
X is equal to
No. Yeah, cos 5t, yeah. A is 1, isn't it? Look, there, A is 1. So you put 1 there, so it's cos 5t. Yes, exactly. Plus 2 sine 5t. Okay, that's your particular solution for that differential equation. Now that's useful solution, isn't it? Because now you know how you know the sine term is double the cosine term, don't you? Okay, you can now sketch a graph of the solution and things like that, can't you? Yeah. These are so far what you've done is what we call initial value problems, IVP. Initial value because you're given when t is 0, x is 0, or dx dt is 0 as well, or dx dt is 10. So when t is 0, the velocity is 0, and the displacement is 0. Okay, those are called initial value problems. But you also have something like called boundary value problems. There was what do you call it? A maths module called boundary value problems. It still exists, but under another name. It's called partial differential equations now. And like I said to physics students last week and astronomy students last week, I think if you look at the entire field of physics in 17th, 18th, 19th, 20th century, it's all full of differential equations. Yeah, that's what you do all the time. I think it should be mandatory for physics and astronomy students to do differential equations. I don't know why it's an option. It should never be an option. They should be forced to do that. That's what they're dealing with all the time. I don't know astronomy so much, but if you're doing physics, you should definitely be doing differential equations, Okay, you definitely should be. I think math students maybe have an argument, maybe they should, and they make math students do it. You math students could argue maybe they don't need it so much. But physics students definitely do need differential equations, okay? Very much so. That's what you're dealing with all the time. Look at, the whole field of physics, and all you'll find is differential equations popping up all over the place. Okay, and you particularly come across boundary value problems. Boundary value problems are those where you take a beam, let's say you take a beam of wood or whatever it may be, or cantilever or whatever it is, okay? You look at one end and you look at the other end. You look at one end and it's got no deflection, at the other end you've got a deflection of, 50 centimeters or whatever it may be, okay? So that's what we call boundary values, the end problems, yeah? When x is 0, the deflection d is 0. When, x is, 2 meters, when x is 2 meters down there, okay, the deflection is 50 centimeters or something. Okay, those are sort of what you call boundary value problems. So you've got something like, these sort of problems, boundary. Or here's one in structures. You put a load and you force it down both ends. Okay, so there's 0, in the middle is something else. Okay, but generally you might have something like this, something which is bending like that. Which is bending. So that's called a boundary value problem. That's your deflection d, and I don't know what it might equal something. Yeah, x is 0 here. You may measure from here the distance, and x is equal to L. Let's say the length of this beam is L. Yeah, you're given that when x is 0, d is 0. Let's say this is equal to d1, and x is equal to L, d is equal to d1. Yeah, those are called boundary value problems. You may come across those, in what do you call it, in physics. And in mathematics as well. Let's look at one more differential equation before we finish off this section. Say you want to solve d squared y dx squared minus k squared y is equal to 0. How would you solve this? How would we solve this one? Yes, our solution is going to be the same. M squared minus k squared is equal to 0. So m squared is equal to k squared. So what is m equal to? Sorry? Yeah, plus or minus k. So what type of solution have we got? What type of solution have we got? Definitely real, yeah. But real in what? Real the same? Real and equal? They're different, aren't they? Minus k and plus k, aren't they? They're going to be different. Minus 2 and plus 2, yeah? So it's real and different. Okay, you've got real and different. So real and different. So what do we get? Y is equal to what? What are we going to get?
Y
Yep.
equal to
Yep.
A
Yeah?
plus B X
No?
and Y. Yeah, A.
Well, let's say M1 is equal to K, yeah? And M2 is equal to minus K,
Sorry,
yeah?
sorry.
Sorry, you can't see. Please shout, you can't see. What do we have? We say it's real and different, so go on, Henry.
A e to the n1.
Or Kx, yeah?
Okay.
K, yeah, Kx, yep. Plus,
Plus b e to minus k.
yeah, plus B to the minus Kx. Again, you've not been given some initial conditions, but that is your general solution. So your general solution for a differential equation of this will give you that general solution, yeah? If you've got d2y dx squared minus k squared y is equal to 0, your general solution is given by that. So really, you know, here what we've done is really solved what we call particular solutions. Any questions on those particular solutions?